Good morning, everybody. Today we are looking at the complex zeros and the fundamental theorem of algebra. This will be a relatively short video, especially by comparison to what we've seen over the last couple of days where we've had to split everything up into two videos. And if I can keep rambling too much, it will be even shorter. So I'm going to jump right into it. Excuse me. A complex zero. Every number that we know can be expressed as a complex number. We've talked about this in the past, but up until a certain point in your education, the real number system is all you've ever known. But what we're looking at now is the simple fact that the real number system is a subset of the complex numbers. And I can say that every number can be written as a complex number because the standard form of a complex number is a plus bi, where a and b are real numbers, but I obviously is the complex root or the imaginary root. You may have heard it sometimes called. And so let's say we had just the number 5. Okay, 5 is a real number, and I can express it as a complex number by writing it as 5 plus 0i. So every number we know can be expressed as a complex number. And that's why we can make the claim that the real number system is a subset of the complex numbers. The fundamental theorem of algebra just says that every complex polynomial function that has a degree of 1 or greater than 1 has at least one complex zero. And we say that now, we make this claim now because we just made the statement that all numbers are a subset of the complex number system. So, like we just said with 5, if 5 was a zero of a polynomial, 5 is a complex solution because we can write it, like I said, as 5 plus 0i. The number of factors that a function may have will be equivalent to the degree of that polynomial. So if it's a degree 2, then it has 2 factors, 2 solutions. If it's a degree 5, it has 5 factors, 5 solutions. Now, some of those solutions may repeat, though. We did see that yesterday in one of the examples where we just we had a quantity and we just squared it because it might have been, I think, x plus 3 maybe. But because that factor appeared more than once, we just put the exponent on it to indicate that it did appear more than once. Conjugate pairs theorem. If we have a complex number, in the case here we see r is equal to a plus bi, then its conjugate is a minus bi, and vice versa. If we have a minus bi, its conjugate is a plus bi. So you're changing the sign on the complex part of the number for the conjugate. And a complex or a polynomial function that has an odd degree will always have at least one real zero. That means it will cross the x-axis at least once. Even polynomials can cross the x-axis, or they can exist entirely above or below the x-axis. So example 1 is just relatively straightforward. It just says we have a polynomial function of degree 5 whose coefficients are real numbers, and it has the zeros 1, 5i, and 1 plus I. Find the remaining 2 zeros. Well, if we look back at the complex conjugate theorem, let me make a list here of what we already have. Here are the zeros that we know. We can clearly see from this list that 5i and 1 plus I are complex. So their conjugates also have to be zeros of the polynomial. Complex zeros occur in pairs, in conjugate pairs for that matter. So 5i, the conjugate of 5i is negative 5i, and the conjugate of 1 plus I is 1 minus I. So the entire list of all 5 zeros is going to be 1 plus or minus 5i and 1 plus or minus I. So there's the entire list. If you wanted to write all 5 of them out individually, you can. Plus or minus will also work because it does indicate 2 different values. Example 2 just says find a polynomial function of degree 4 whose coefficients are real numbers that has the zeros 1, 1 and negative 4 plus I. We have seen problems like this before where we're given the zeros and we're asked to find the polynomial or a polynomial that could have those zeros. So again, if we make a list of the known zeros, we have 1, 1, and then we have negative 4 plus I. That's all that we're given. But we know that this has to have 4 zeros because it's a degree 4 polynomial. This negative 4 plus I is complex, so its conjugate must also be another one of the zeros. So it's the negative 4 minus I was the one that we're missing. So now if I take all of these and write them as factors, I have x minus 1 times x minus 1 times x minus negative 4 plus I, and then I have x minus negative 4 minus I. So there is the factored form using each one of the zeros that we were given and the one that we had to find. And now we're going to go ahead and kind of multiply these out and come up with the polynomial. So I'm going to go ahead and multiply the x minus 1's together first, and that's going to be x squared minus 2x plus 1. Let's distribute the negatives through here to simplify these a little bit. I get x plus 4 minus I and x plus 4 plus I. And then when I multiply these two together, I'm going to go ahead and bring down the x squared minus 2x plus 1 because we're going to work with it in a second. I'm going to get x squared plus 4x plus ix. Now I'm going to use the 4 and distribute, and then I get 4x plus 16 plus 4i. And now I'm going to distribute the negative I, and that's going to give me negative ix minus 4i minus I squared. So let's clean up the right-hand side a little bit more by combining like terms where we can and simplifying what we can. Nothing combines with the x squared. I have a positive 4x, and that's going to be it, so I get a 8x. Positive ix, negative ix, they cancel one another, so I don't have to worry about that. I have a positive 4i and a negative 4i. They also cancel. And then I have this 16 and this negative I squared. Now, if you recall, I squared is equal to negative 1. So this is minus a negative 1. So we can rewrite this as plus 1. So I have 16 plus 1 gives me 17. And then now I can multiply these two trinomials here that I have now. I can multiply them together to generate the polynomial or a polynomial of degree 4 that has the given zeros. So I'll multiply through by the x squared first. Then I multiply through by the negative 2x. And then I multiply through by positive 1. And now I combine like terms and clean the equation up a little bit. Nothing combines with my x to the 4th. 8x cubed minus 2x cubed is going to be 6x cubed. 17x squared minus 16x squared is 1x squared. Plus x squared will be 2x squared. Negative 34x plus 8x is going to be negative 26x. And then I have the constant 17. So this is my polynomial of degree 4 that has the zeros 1, 1, negative 4 plus I, and negative 4 minus I. And this is our last example. We're going to kind of put together what we did yesterday, coupled with what we're learning today, and find all of the zeros of this polynomial. Yesterday we were finding the real zeros only. Today we're going to find all the zeros. So we're going to use some of the same techniques that we began with yesterday. The first step is that we notice the degree of this polynomial is 4. So that implies then that this has 4 zeros that we will find. If we don't find 4 zeros, then we have made a mistake somewhere and we need to go back and look at our method. The second step will be to apply Descartes' rule of signs to help us determine what kind of zeros exist. So the first thing we want to do for the positive real zeros is we count the sign changes in the original function. So we notice positive to positive, right here, there is one sign change. So that means that they has one positive real zero. I don't need to rewrite that. We have one positive real zero. And then for the negative real zeros, we take our function and we evaluate it at negative x. So let's do this. And what we get is 3x to the 4th minus 5x cubed plus 25x squared minus 45x minus 18. And we count sign changes. There's 1, 2, 3, and that's it. We get 3 sign changes. So that means that we have 3 or 1 negative real zero. So from here we can go on and we can do the rational zeros theorem, which will be our third step. And remember, the rational zeros theorem, we look at the constant and the leading coefficient and we list the factors. So for our value for p, which happens to be 18, the factors of 18 are plus or minus 1. And I believe that's all of them. Then we list our factors of q, which is 3 in this case. So we have plus or minus 1, plus or minus 3. When we put this together, p over q, we're going to generate all the potential rational zeros that exist for this particular polynomial. So remember, the entire list gets placed over 1 first. So I'm not going to put everything over 1 because we know that it'll all simplify back down to its original value. And then now I divide everything by 3. So I get plus or minus 1/3, plus or minus 2/3. I ignore 3 over 3 because we already have 1 in the list. I ignore 6 over 3 because that reduces the 2, which is in the list. I ignore 9 over 3, which reduces the 3. And I ignore 18 over 3, which reduces the 6. Remember, we do not use repeated zeros in the function. Then the next thing that I would want to do is start picking numbers from the list and substituting them into my given function. And I find the first value that I can find, that I come up with, that gives me 0 as an answer, will help me find the first factor. And just like I did yesterday, I've gone ahead and I've worked this one out. I'll tell you my process. I started out with positive 1. I substituted it in and found that I did not get an answer of 0. So then I tried negative 1. That didn't work. I tried positive 2. That didn't work. But when I substituted in negative 2, I did find that the answer does simplify to 0. And I'm going to express that to you right here. Let's see. And then when I clean this up, negative 2 to the 4th is 16. 3 times 16 is 48. Negative 2 cubed is 8. Is negative 8 actually. plus 5. So that would be positive 5 times negative 8 is negative 40. 4 plus 100 minus 90 minus 18. And when I add all these together, here I get negative 8 plus 100. Right, negative 8 plus 100 is 92. 92. Wait a second. I don't know why I was getting so worked up. I was thinking too far ahead. 48 minus 40 is positive 8. 100 minus 90 is 10. And then we have minus 18. 8 plus 10 is 18. Minus 18 does, in fact, equal 0. So what this implies then is that x plus 2 is a factor of our polynomial. And from here we can do synthetic division, because then we're going to generate the depressed equation that we have talked about previously through the synthetic division. And I will do that with negative 2. And then I'm going to put the coefficients in for my original function. And then we just complete the synthetic division. Remember, you bring the first term straight down. So there's the 3. Negative 2 times 3 is negative 6. We'll add these two values to get negative 1. Negative 2 times negative 1 is positive 2. And I wrote down 3. Add those together to get 27. Negative 2 times 27 is negative 54. When I add these together, I get negative 9. Negative 2 times negative 9 is positive 18. This does end up being 0. And because this is the depressed equation, we started out at degree 4, so now we're at degree 3. There's our constant. So we're now looking at 3x cubed minus x squared plus 27x minus 9. And what we can do with this is we can do factor by grouping. So we look at the first two terms, they share an x squared in common. So we factor that out, that gives us 3x minus 1. The last two terms, they do share a 9 in common. And we factor that out and we get 3x minus 1. So this factored, the depressed equation factors into x squared plus 9 and 3x minus 1. And then we pull down the factor that we found previously, which happens to be x plus 2. And this generates the factored form of the given function at the beginning of the problem. Now when we find the zeros, the x plus 2, we already know that 0 is negative 2. From this one, we can see that 3x minus 1, when we set that equal to 0, we get a 0 of 1/3. The x squared plus 9 is the one that's going to generate our complex zeros. So we have one negative real 0, one positive real 0. The remaining two zeros are going to be complex. So we take x squared plus 9, set it equal to 0. We subtract the 9. We take the square root. And then we know the square root of negative 9 is going to be plus or minus 3i. So our complete list of zeros is negative 2, 1/3, and plus or minus 3i. And there are the zeros for the function that we were given for example 3. Here are your suggested problems. Take a look at those. Remember, if you do have questions, you are free to ask any questions you have of me on this stuff, and I'll do everything I can to help make sure you understand it as best as humanly possible. Hope you guys are having a great day, and I will be seeing you around 2 o'clock.